Hello guys, welcome to this class. In this particular class, we are going to be discussing the Earth's magnetic field. The Earth's magnetic field, you know that the Earth behaves like a magnet. So we are going to look at the Earth's magnetic field. Then there are some other areas that we'll look at. We'll look at angle of dip, magnetic meridian, angle of declination, and all that. Then we'll also look at magnetic flux, magnetic force on a charge in a magnetic field. Then we'll now solve some problems. Okay, so this class is going to majorly focus on the Earth magnetic field and the various um, properties. All right, so please get your writing materials ready so that we can go straight to our class. But before that, please, if you have not subscribed to our channel, please subscribe to the channel, click on the notification bell so that whenever we upload a new video, YouTube will notify you. This is Nobleman Science Tutors Online, and we are teaching physics for now. In a short while, once we complete this series in physics, we'll move over to other subjects. Is that okay? So please give us a thumbs up, give us a like, give us a positive comment so that you can continue to encourage us. If you have any challenge, if you have any question, any challenge, please click on the WhatsApp link down the video, and then you can place your question on the WhatsApp chat platform. Okay, so please get your writing materials ready so that we can go straight to our class for today. So as I said, we are looking at the Earth's magnetic field. So how does the Earth behave? The Earth actually behaves like a giant piece of magnet, right? With the South Pole pointing the northern geographic pole and the North Pole pointing in the southern geographic pole. So if you are a geography student, this can represent the Earth. Then the Earth behaves like a magnet. So if you look at this magnet, the South Pole are pointing towards the north, and the North Pole they are pointing towards the south. We are told that that is how the Earth actually behave. So because of this behavior, when a magnetic needle is suspended on the Earth freely about its center and away from any other magnet, the bar magnet will settle, or the needle will settle with its axis pointing in a north-south direction. So assuming this is the needle, assuming this is the magnetic needle, when the magnet is suspended freely, if it is suspended freely, you find out that the magnet will settle in the north-south direction. Okay, so if you have your compass to show you the cardinal point, you can actually use that to know the direction in which the needle will settle. But it does not actually settle straight, it settles at an angle. Okay, it settles at an angle to the Greenwich Meridian. Okay, so it settles at an angle to the geographic north. Settles at an angle to the geographic north. Okay, so this is just the behavior of the Earth that is described here. Now, for the behavior of the Earth, we have some phenomena that are described, and that are called magnetic elements of a place. Magnetic elements of a place. So that's what we want to discuss now. So what are the magnetic elements of a place? The magnetic element of a place determines the magnetic field of the Earth at each place. These magnetic elements are the angle of declination, the angle of declination, the angle of dip, and the horizontal components of the Earth magnetic field. Okay, so what is the angle of declination? The angle of declination is the angle between the geographic and magnetic meridian. So if you look at this picture, you'll see that this is the geographic meridian, and then this is the magnetic meridian. So the angle between the two is known as the angle of declination. Okay, so Mariner uses this angle in calculating their bearing. All right, Mariner uses this angle to calculate their bearing. Then we have the magnetic meridian. The magnetic meridian is a vertical plane passing through the magnetic axis of a freely suspended bar magnet at rest under the influence of the Earth's magnetic field. So this is the magnetic meridian. Then also the geographic meridian is a plane containing the geographic north. Okay, so this line here is actually the geographic north. This is geographic north. So it is a plane containing geographic north and south pole of the Earth. The geographic north and south pole of the Earth. This is the geographic meridian. So all these ones plus the angle of dip and horizontal component of the Earth makes up the magnetic element of a place. Okay, so these are some basic terms that we need to take note of when we are discussing the magnetic field of the Earth. So the angle of dip is one of the magnetic element of a place, and the angle of dip is the angle between the direction of the Earth's resultant magnetic field and the horizontal. So if you look at it, you see this is the horizontal. Then a needle that is placed here will show you the Earth's resultant magnetic field. This is the direction of the resultant magnetic field of the Earth. So the angle between the horizontal and the direction of the resultant magnetic field of the Earth gives you the angle of dip or angle of inclination. The angle of dip is the same thing as angle of inclination. So this is what I've also represented. This is the horizontal, and then this is the angle at which a freely suspended magnet settles. So the angle between the horizontal and the resultant of the horizontal and the resultant of the Earth magnetic field gives you the angle of dip or the angle of inclination. Okay, so this is supposed to be angle of inclination, right? So this angle of inclination, that's a typo error. So that is angle of inclination or angle of dip. Okay, angle of dip. All right. So this is the angle of inclination or angle of dip. The angle between the horizontal and the Earth's magnetic and the resultant Earth magnetic field. That is the angle of dip. All right. So we also mention the horizontal components of the Earth's magnetic field. The horizontal component H of the Earth's magnetic field at a point is the magnetic force along acting in a horizontal direction, while the vertical component of the Earth's field at a point is magnetic force acting in a vertical direction, and that is what is represented by this direction. Okay, this is the Earth's horizontal magnetic field. So the angle between the horizontal and the Earth's horizontal magnetic field gives you the angle of dip. That is what we just discussed now, right? So if you look at this drawing, you find out that the horizontal component represented by cos theta is equals to h over b. You know, cosine is adjacent over hypotenuse. Okay, so that's it. So h is equals to b cos theta. The same thing too is done for the vertical component. Vertical component v is equals to b sin theta. Okay, vertical component of this is equals to b sin theta. Right, then we can actually do this so that the angle of dip If the angle of dip is this, then tan theta is equals to V over H. So if we take these two equations, we'll find out that B, for the horizontal component, B is equals to H over cos theta. H over cos theta. Because maybe that's H over this. Then for the vertical component, you have that B will be equals to V sine, for V over sine theta. Okay, so since we have the value of B, which is the earth magnetic resultant field, we can actually equate these two together to have H over cos theta equals to V over sine theta. So if you do a rearrangement of this particular equation, you are going to have that V over H is equals to sine theta all over cos. So we know that sine theta over cos theta is equals to tan theta. Okay, so that is what we have here. This is what we have here. Alright. So the angle of dip can actually be calculated from the values of the resultant force along the horizontal and the vertical axis, as the case may be. Alright, so that is just that. I hope this one is clear. Then magnetic fields on a bar magnet on the earth magnetic flux. Okay, so in this particular section, we are looking at the neutral points. The neutral point is the point at which the magnetic force due to the earth's field is equal and opposite to the magnetic force due to the field of the bar magnet. So what that means is that the resultant magnetic force at this point is equals to 0. Okay, it means that the resultant point are equals to 0. So when a bar magnet, if the north pole of the bar magnet is pointing north, you have your neutral points at the sides like this. So these 2 points, they are neutral point, this point and this point. Then when the southern pole of the bar magnet is pointing north, when the south pole is pointing north, you have your neutral point at this point and this one. You need to take note of this drawing because these are the type of question they bring during your in your objective question in JAM and in WAEC. So take note of this so that you will know where your neutral point is. What you will look at when you are giving this type of question in your objective is look at the poles of the magnet. That's where you get confused. Look at the poles. If the northern pole is pointing north, then your neutral point should be at the side. If it is the south pole that is pointing north, your neutral point should be at this edge, as the case may be. I hope that is clear. Okay, so thanks, and I hope you follow through with that. Magnetic force on a charge in a magnetic field. So if a charge is placed in a magnetic field, the magnetic force on that charge is given by this equation. So the magnetic strength of a magnetic field is a vector quantity called flux density or magnetic induction, represented by a letter B. So if theta is the angle between the magnetic field direction and the direction of motion of the charge. So assuming you have, this is the magnetic force, and then this is the velocity of the charge, and then B, this, then the force on the charge is given by force equals to charge times velocity times magnetic flux density times sine theta. Sine theta is the angle between the force and the magnetic flux. Okay, so theta is the angle between the force and the magnetic flux, or direction of magnetic flux. So Q, as I said, is charge in coulomb, V is velocity of charge, B is the flux density of magnetic induction. The unit is Tesla, and the unit is Tesla, and 1 Tesla is equals to 1 Weber per meter square. F is the force in Newton. Now, in some cases, you can write this VB sine theta as V times B. Okay, therefore VB sine theta is equals to V times B, and then this equation comes to look like this. So if the angle between V and B is equals to 0, then F will become 0 too. So the force will be 0. That is if they are in parallel. Okay, if the direction of motion is in parallel to the magnetic flux, then the force will be equals to 0. But if they are at an angle of 90 degree, then the force will be equals to Q times V times B, which is the maximum force that you can obtain. Right? Then for a conductor of length L carrying a current of I amp in a magnetic field that has magnitude B, the force is given by the magnetic flux times the length times the current times the sine of the angle that is formed. Okay, so take note of this equation. Then another equation that you need to take note of is that magnetic flux is given by B A cos theta, where B is equals to magnetic field, A is area, and theta is angle between A and B. Another equation is electric flux is electric field times surface area. So E is electric field and S is area of the surface. So here we have looked at some equations, and we try to solve some problems in a short while. Alright guys, so this is a sample question that I need to solve so that we will be able to drive on all the equations that we have discussed so far. Alright, so we have said that okay, this question says that calculate the magnitude of the force experienced by an electron projected into a magnetic field of flux density 10 Tesla with a velocity of 5.0 times 10 to the power 7 meters per second and in a direction 90 degree, 60 degree and parallel to the magnetic field. The electron charge is given by 1.6 times 10 to the power minus 19 coulomb. This is a NECO examination question, and I think this is a theory question. Now, for you to solve this problem, first write that the force is given by the quantity of charge multiplied by the velocity multiplied by the flux density times sine theta. Okay, so just write that down. Then for this particular question, you are given Q to be 1.6 times 10 raised to power minus 19 coulombs. You are given B to be 10 Tesla. You are given velocity to be 5.0 times 10 raised to power 7 meters per second. Okay, so the angle between them is what is varied. Theta is now varied, so we'll take it one by one. At 90 degrees, we'll look at it. At 60 degrees, we'll look at it. Then when they are in parallel, we'll also look at it. So at 90 degrees, 1. So you see at 90 degrees, F equals to the Q times V times B times sine 90 degrees. So substituting into this equation, you are going to have Q to be 1.6 times 10 raised to power minus 19 times velocity velocity is 5 times 10 raised to power 7 times b, which is 10, times sine 90 degrees. Sine 90 degrees equals to 1. Okay, so by the time you work this out, this point 6, you have that force is equals to 8.0 times 10 raised to power minus 11 Newton. Okay, so press that out from your calculator, and this is what you are going to have. So when the angle between them is 90 degrees, this is the force that is experienced by the electron. Then at 60 degrees, you add that force will be equals to 1.6 times 10 raised to power 19 multiplied by 5 times 10 raised to power 7 times 10 times sine 60 degrees. Sine 60 degrees will give you 0.8660. So by the time you multiply that out, you will have 6.9 times 10 raised to power times 10 raised to power minus 11 Newton. Alright, so that is it. Then when they are in parallel, it means that the angle between them is equals to 0 degrees. So in that case, it means that F will be equals to 0. Okay, so when they're in parallel, F will be equals to 0. That was what we discussed before. So this question has actually touched on all the aspects of this this calculation on magnetic field, or magnetic force in a charge in a magnetic field. Is that okay? So I hope you can relate with this, and this is quite simple. Alright, so please try your hands on any other question that you can see relating to this particular topic. So guys, this is your test your understanding page. Please solve these problems, check your textbook for some other questions, and also solve, so that you continue to improve in your knowledge. Right, so thanks. This is where we're ending our class for this particular segment. So before I leave, please, I will still continue to encourage you. Please subscribe to our channel, give us a like, give us a thumbs up, click on the notification bell so that when we upload a new video, YouTube will notify you. Right? We are glad that you are following us. Continue to give us a thumbs up and a like and positive comment. Also invite your friends to come and enjoy what you are enjoying in YouTube. So please have a nice day, and enjoy your studies and yourself. Hope to see you in our next class. Thanks.